All right, let us begin talking about circulation. This is, again, movement of air, and we're going to be talking about specifically wind and how wind is generated through the circulation of the atmosphere through convection. We'll talk about how the winds curve due to the Coriolis effect, and we'll look at the jet streams. We're also going to talk about the air masses that are moved by these winds and the characteristics they take on depending on where they exist. Where the air masses meet, we call them fronts, and we'll discuss the different types of fronts. And then we'll look at weather systems that pass through the center of our country because of all these air masses interacting with one another in fronts and how this creates kind of low and high pressure. So, circulation. Let's begin with wind. Really, where it starts is that solar radiation hits the equator and makes the air rise because the air is warm. The air becomes less dense because the air molecules are spread out in warm uh, air, and it begins to rise. If you're standing on the surface and you have air molecules rising away from you, you feel lower pressure. There's not as many air molecules pushing on you, so the pressure is lower. Um, and again, really the driving force for all convection and circulation and air movement in the atmosphere is the sun and solar radiation. Um, so as the air rises at the equator, we have the air sinking at the poles because cold air sinks. Cold air has general tendency to be moved. The molecules are moving slower, and so the molecules are more packed together. And so if you're standing on the North Pole, you typically have air molecules sinking towards you. And that would be then a high pressure situation where you have more air molecules packed around you than normal. Um, as it stands, then, if you have air rising at the equator and air sinking at the poles, you're going to have a surface circulation. The surface wind is going to pass from high pressure to low pressure, and thus you have surface winds moving from north to south. Likewise, as the air is replaced in the upper levels, you have an upper level wind circulation as well. So this is how convection, hot air rising and cold air sinking, produces surface wind. Now, as the wind blows from the North Pole to the equator, what happens is the Earth actually begins to, or the Earth is constantly rotating, right? So because the Earth is rotating, the path of the wind actually curves. It curves in a clockwise direction. And this effect of the winds curving because of the Earth's rotation is called the Coriolis effect. It's named after a scientist who studied it. But um, wind curves because of the Coriolis effect. Airplanes curve because of the Coriolis effect. If you're flying in an airplane from the north towards the south in the northern hemisphere, you have to aim um, a little bit east in order to make it to your destination because the Earth is going to curve and rotate as you move, and so your actually overall path is going to be curved. The winds do the same thing. So imagine wind starting at the North Pole and trying to make it to the equator, but the wind kind of keeps curving. What's going to happen eventually is the wind is actually just going to completely curve around and swirl. And so the wind that starts at the equator doesn't make it. And so you have this own little mini cell, mini convection cell here up in the north. Well, then you have to start a new convection cell here in the middle latitudes. And again, the winds curve so much that a new convection cell has to start. And so, because of the Earth's Coriolis effect, because the Earth is rotating, the surface winds break the Earth's circulation up into three separate convection cells in the north and three separate convection cells in the south. That actually provides for three different kinds of surface winds. We have the trade winds in the lower latitudes, the westerlies in the middle latitudes, and the polar easterlies in the higher latitudes. Here's another look at them. You can see that this northernmost cell up here is called the polar cell. The middle latitude cell is called the Ferrel cell, named after a scientist who studied it. And same with the Hadley cell. A scientist described it. So this is a Hadley cell in the lower latitudes. And the trade winds, the westerlies and the polar easterlies are labeled in the southern hemisphere, but it's the same in the northern hemisphere for both. So hot air rising, cold air sinking causes surface wind. But because the Earth is rotating, the surface wind curls around so much that we have little convection cells that form in different spots on the Earth. At the conjunction of the convection cells where air is rising, that's where we have storms. So the air is rising most at the equator and around the equator, and so as you might expect, you have lots of clouds and storms there. In fact, of course, the tropical rainforests are near the equator there, right? The next convection cell, the Ferrel cell, actually circulates in this direction, and the air rises more in the middle latitudes. They call that the polar front, but there's rising air there as well. So you have clouds and storms around the equator and clouds and storms around the so-called polar front. And the storms in our area, they come from the polar front. And here's a look at the cells from the side, what they might look like. Now, notice that the polar cell here, it's smaller. It's not actually, it doesn't have any less air. It's actually got more air, but the air is more dense because the air is cold. And so that's why it looks a little lower. It doesn't rise up as much. The Ferrel cell is having the same amount of air, but spread out a little bit more. It's a little bit bigger. And the Hadley cell is the biggest here, spreading air out because it's the warmest. An interesting side note of all this is that because the polar cell has higher pressure than the Ferrel cell, air tries to rush across to balance the pressure difference. As this air rushes across, the Coriolis effect changes its direction and moves it sideways. And so what happens is that you get a river of air, of fast moving, high velocity air um, at the top of the junction between the Ferrel cell and the polar cell. This is called the polar jet stream. So jet streams are basically relatively narrow bands or rivers of air. They're about 300 miles wide and about 3 miles thick, and they are winds are can be up to 370 miles an hour. I mean, they're really fast. This pressure difference is so stark that there's a very powerful force of wind moving in. And again, thanks to the Coriolis effect, it rivers around the globe in bands, and they're about 8 miles up from the surface. Okay, so these are our jet streams. There's also one between the Ferrel cell and the Hadley cell. That's called the subtropical jet. That's usually a further south of us, and so we don't have weather influenced by that. We usually have weather influenced by the polar jet. You may have seen this on the weather reports. Here is the jet stream, and they often show the jet stream to indicate where the boundary between that polar cell with colder air and the Ferrel cell with the warmer air is. Also of note is that the jet stream, as it meanders, can actually help provoke storms and move air masses. So, as the jet stream has these little kinks and meanders, those meanders and kinks actually help draw air upward, producing stronger clouds and storms. So that's wind. That's essentially the circulation in our atmosphere. Now, the wind, it pushes masses of air. So let's talk about those air masses. The air above the surface of the Earth takes on the characteristics, of course, of the area just below it. And so, for example, the area in Canada and around our area would be called would take on the characteristics of our area. So it would be cooler air. It would be air that's more dry because there's mostly land around us. Um, the air, for example, over the oceans in the north east or northwest of us, of our continent, would be cooler, but they would be more moist, right? They would have more moist air. And likewise, the warmer air toward the south, if it's over the oceans, it would be moist. And if it's over the land, it would be dry. And so each of these are called air masses. They're basically bodies of air that hang around over a top of a surface of the earth. And they also get pushed around by those winds, those surface winds, those westerlies and polar easterlies we talked about earlier. The dry air that's above land, we call it continental. And it can be anywhere, right, in the north or south. The moist air we call maritime for sea, moist. The warm air we call tropical, and the cold air we call polar. Now, there's a couple more designations not listed here. There is one called Arctic for really cold, and there is one called equatorial for really warm, but they don't really impact our country, so just left them out. You can learn more about them if and when you go into meteorology deeper. Now, the air masses are actually named by a combo of the humidity and the temperature. So, for example, the air masses over the northwest in the Pacific Ocean or the northeast in the Atlantic Ocean, those are called maritime polar. And they're also abbreviated with letters, but they abbreviate the humidity first with the lowercase letter and then the temperature with an uppercase letter. So the maritime polars I just described would be lowercase m, uppercase p. So very interesting, right? If I had to ask you what would be the air mass that's typically around us, you would say continental polar. And if I asked you what the abbreviation was, you'd say lowercase c, uppercase p. All right. And so that's typically the storm systems that pass through the center of our country are generated because this continental polar air coming from Canada kind of sweeps down across our country thanks to the westerlies. And it's that cold air is dense, and so it plows warm, moist air up above it, producing clouds and storms. Where does the warm, moist air come from in the center part of the country? The Gulf of Mexico. The air over the Gulf of Mexico is a maritime tropical air. It wafts in and kind of floats up towards us northward. And when the Canadian air comes through, it plows it upward. Let's talk about how those air masses are moved and how they bound the boundaries of them, which are called fronts. Here's a kind of a depiction of what I was just describing. That continental polar air from Canada usually sweeps down, and the maritime tropical air from the Gulf of Mexico wafts up. And when the continental polar comes through, it usually plows that warm, moist upward, creating clouds and storms. Remember, rising air equals clouds and storms. Meanwhile, there's also a third air mass that likes to come into our country, but it usually hangs out in the south. It's a continental tropical one from Mexico, on the high plateau of Mexico, sends that air in, and it actually works to help force the air upward a little bit, which actually creates some more tornado action and more thunderstorm action in places like Texas, Oklahoma, Kansas. That's why they have so many down there, because not only do we have cool, dry air from Canada, but we also have got that continental tropical air helping to force air upward. But the boundary between these air masses are called fronts. And you can see pictured here a cold front and a warm front. All right. Cold fronts are basically where cold air is advancing into other air. And that would be called a cold front. It's depicted by these blue triangles and the triangles point in the direction of the frontal movement. A warm front would be where warm air pushes its way into a region, and those are indicated by this line with half circles that are red. Usually, when cold air comes plowing its way in, clouds and storms are produced. And when warm, moist air pushes its way, excuse me, when moist air pushes its way in, you usually get steady rain. And so fronts are labeled actually, as I described, with symbols, and so we'll talk about that. And they actually identify the type of air and the direction of movement. So here they are. The warm front is the red half circles. The cold front are the blue triangles. There's a front called an occluded front. That's actually kind of like the end stage of a cold front plowing through. We'll talk about that in a second, but it's half circles and triangles. So it's kind of like warm and cold air have already met there. And then a stationary front is where the air on both sides isn't really moving anywhere. It's just kind of warm air sitting on one side of the front, cold air sitting on the other side of the and I'll talk about each of these here, starting with the cold front. Cold front is really what produces all this thunderstorm action. Cold air is dense, and as it advances, it plows warm, moist air upward pretty vigorously, and that produces our clouds and storms. You can see the blue triangles here indicating the direction of the front movement. Warm air does intrude on cold air, but again, because cold air is more dense, the warm air kind of just pushes along and glides up over top of the cool air. And as a result, you get these lots of clouds form, and in some cases, steady precipitation. Occluded fronts are where that cold front kind of pushes its way in, pushes the warm air up, and then on the other side of the warm air is cool air. And so you basically have cold air on one side, cool air on the other with warm air above. And that's shown in a side view here. That's an occluded front. It's kind of like the end stage of a storm system that's kind of passed through our country. And then we have a stationary front. Again, cold air sits on one side, warm air sits on the other. They could sit there for days without advancing on one another. Sometimes you get a little light precipitation, but really you don't get any weather until a kink develops in the stationary front. Like there's like a little bubble or a kink. They actually call it a wave. And so let's talk about that. Waves actually produce mid-latitude cyclones, which are the storm systems that pass through the center of our country. Here's a picture of a wave, what we would call a wave here. And then here's a stationary front some more. There's a little bit of a dip here and then another kink or wave. And it's at these waves that cold air starts to circulate in and push in on the warm air, and the warm air starts to circulate up as well. This is what it might look like with the cold air rushing in and the warm air pushing its way up. When that happens, you actually get a circulation. Because of the Coriolis effect, this wind has a tendency to start to swirl around these kinks or waves. And when it swirls, it actually kind of like all swirls into the central point on the kink. And the air then swirls upward from there. And so if you were standing in that big L, red L, what you would be standing in is a situation where air is rushing in on you, but it's actually rushing in and swirling upward. So you would feel lower pressure in that area. Low pressure is rising air, and rising air is clouds and storms. So what you would see is you would see strong precipitation here along around the L. You would see strong precipitation along the cold front where it's plowing warm, moist air upward, and you would see significant precipitation where the warm air is forcing in on the cooler air and kind of floating upward. This whole scenario, a cold front pushing in, a warm front pushing forward, and air draining inward and upward on a low pressure, that's called a mid-latitude cyclone. And these are basically kinks in the polar front that move along through the center of our country, producing thunderstorms and weather. Here's a picture of one. This would be a big one, noting that there's the cold front would probably be right along in here. The warm front would probably be more up here, and then the low pressure would be right here. Here's a look at what it might look on with frontal boundaries drawn in. The cold front, the warm front, and then the low pressure. You can see it looks like almost like a comma, a big comma. This is a mid-latitude cyclone. Thunderstorms are produced with mid-latitude cyclones. Lots of rain, winds. So the normal storm systems we see come through our country are these. And here, just to summarize, before we move forward with this, you've got your stationary front. You've got a wave develop. Cold air begins to swirl in. Warm air begins to swirl up. Eventually, you get this nice swirl motion, and you get the low pressure here. And then it spins itself out, and the fronts kind of reconnect and form another stationary situation. All right. We've been saying low pressure a lot. Let's end with defining pressure with both low and high. So as that air swirls in to a low pressure center due to the Coriolis effect, it'll actually start to swirl in and swirl upward. They call that surface convergence. And as the air converges toward the surface, it'll actually, as it swirls upward, it'll produce clouds and storms, stormy weather. Rising air does that. And typically, a lot of times when you have these stronger storms, you have divergence in the upper level winds. The upper level winds are actually helping to draw air, suck air upward so that it can more vigorously swirl upward. So low pressure centers are usually associated with mid-latitude cyclones and our stormy weather. High pressure systems, on the other hand, are where air converges in the upper levels and actually flows downward. It hits the surface and wafts out in curving directions thanks to the Coriolis effect. So it swirls downward, where it hits the surface and curves outward. This, if you were standing here, you would feel more air molecules than usual. That would be then considered high pressure. And when air sinks, it does the opposite of rising air. When air sinks, it actually dries out and is clear. So sinking air equals clear weather. So if I were to summarize, I'd show you a picture like this: cold and dry and bright and sunny with high pressure as the air descends. And as the air rises, it cools and condenses to form clouds and storms and rainy weather. So that is low and high pressure. So, ladies and gentlemen, atmospheric circulation involves convection, hot air rising, cold air sinking. This produces surface winds. The surface winds curve on the surface because of the Coriolis effect, producing separate convection cells, at the top of which there are major pressure imbalances that have rushing air that, thanks to the Coriolis effect, turns east westward and flows like a fast moving river of air, the jet streams. Meanwhile, air masses hang out above the surface of the land and the surface of the water, and they are wafted to and fro by the surface winds. When they interact or meet, it's called a front. As they push forward, cold air pushing forward is a cold front, warm air pushing forward is a warm front. After they've zipped up and kind of connected, they are occluded fronts, and stationary fronts are where they sit next to one another. Those waves in the stationary front can produce mid-latitude cyclones, which are advancing cold fronts and advancing warm fronts and low pressure systems. And we noted that low pressure is equal to rising air and clouds and storms, and high pressure is equal to sinking air and clear weather. So that, ladies and gentlemen, is atmospheric circulation.